Hello everyone, welcome to part 2 of this problem. The problem states that time-dependent one-dimensional heat conduction through the thickness of a rocket motor casing. The inner surface of the casing is exposed to hot combustion gases while the outer surface is exposed to ambient air at 300 Kelvin. To run the simulation, the user must provide inputs for the time step, total simulation time, special step, and initial hot temperature caused by the gas combustion. The importance of the study is to prevent the catastrophic failure if the material chosen was not suitable, leading to structural failure and case rupture. To understand the thermal stress and fatigue of the material while being exposed to a high temperature, to help selecting the best material with suitable thermal properties. This time, we will be using the implicit method to solve the problem. It is because the implicit method is unconditionally stable for linear problems. No strict requirement on time step size for stability. Step size does not matter. More robust, especially for stiff or long time simulations. Here is the derivation of the implicit method. Now this is the programming part of the implicit method to solve the parabolic PDE. Based on the program shown before, the user needs to input the number of spatial intervals, number of time steps, hot temperature from the combustion engine, and the total simulation time. The outcome, the user is expected to have the result table with the intervals, positions, temperature, and approximation error across the casing of the rocket. The user will also expect to have the graph involving the temperature distribution between the cost interval and find interval across the casing of the rocket. Here, based on the input obtained from the user, the graph displayed shown that the find and the grid cores have similar graphs, which means the solution is convergence. Next, we can see the approximation error shown. It is small, so the solution is convergent and also reliable. Based on the results achieved in the previous slides, we can see that this method can be made first order or second order accurate in time, suited for long-term simulations, stiff systems, and problems with fine spatial grids. High efficiency for long-term simulations as fewer steps due to more work per step. Convergence improved with finer meshes and smaller time step. Effect of step size only affects the accuracy but not stability since it is unconditionally stable. Programming difficulty is, however, is high because we need to solve the matrix involving to solve the problem compared to explicit method. For the advantages, it is unconditional stability regardless of time step size, suitable for problems where fast and slow processes coexist, for example stiff problems, more accurate with Craig-Nicholson method due to combining implicit with midpoint approximation. However, there are limitations. Higher programming complexity as it needs good handling of matrix form equation, less accurate for very large time steps, and lastly, high computational cost per step. In summary, I have contributed to solve the parabolic PDE engineering related problem involving the temperature distribution of casing of a rocket. I learned on how to use the MATLAB to run the simulations and going through the difficulty of programming the codes. Furthermore, I acquired further understanding on the engineering applications involving the parabolic PDE using the implicit method, hence finding its limitation and advantages. Thank you.